in the realm of computer security. Not to minimize the fact that a lot of security issues we have to deal with are internal threats, our own employees, for example, and issues relating to fraud. And we'll come back to that. We'll talk much more about that in the upcoming weeks. But definitely a key aspect of many of the problems that we're faced with in industry today relate to the fact that we're connected. So that we're connected throughout using the internet. So we're globally connected. And so this brings a whole slew of different issues that are important to us. And so in order to have this common sort of baseline understanding, there's a few really important concepts that we have to understand. First, there's a theoretical model, the OSI Reference Model, that that's going to help us to understand networks and how computers communicate. And then, of course, there's the physical aspects and the logical aspects of networks, and the TCP/IP protocol that everyone is using today, and then some tools and some other control aspects. So first, let's start with this OSI, so the Open System Interconnection Reference Model. So this is a really important model to use as a reference to understand how networks operate and how computers, software, and hardware information systems communicate across networks. So basically, we're breaking down the whole process into 7 layers, starting at the bottom of the stack that we see here with the physical layer. So the physical layer is really about getting data across these cables. So the physical layer is responsible for the physical operation of the network. It translates the binary ones and zeros of the computer language into the language of the transport medium. So if we're dealing with copper wiring, like a Ethernet or the standard, twisted pair networks that we're dealing with, that the physical layer, we're talking about how we're transforming the ones and zeros into electrical signals. If we're looking at fiber optics, then we're looking at the physical layer of how we're transforming the ones and zeros into light. And then another common networking scheme that we use quite a bit today, wireless, Wi-Fi, or wireless local area networks, WLAN. At the physical layer, we're looking at how are we transforming the ones and zeros into radio frequencies or RF waves that are being transmitted on RF. So, waves having ups and downs. And so that's how we make the ones and zeros. With the copper wire, the switch is on, the switch is off. There's a power, there's no power. That's basically ones and zeros. The light is on, the light is off with fiber optics. So all of this is happening at the physical layer. Then the layer 2 is the data link. So this has more to do with the addressing of the physical information. So this layer is responsible for transmitting information on computers connecting on the same local area network. So it uses in order to do that, it uses something called the MAC address, or the Media Access Control addresses. And this is a physical, if you have like a wired copper twisted pair network, the MAC address is actually physically put on sort of a electronic component called an EEPROM, or a programmable read-only memory. In some cases can be erased. That's the EEPROM, or a PROM, it just can't be erased. So it's hard-coded on that. And that's a globally unique address. So, if we're trying to physically identify a transmission from a machine, the MAC address on the global scale is a unique address. So you can, something maybe we can talk about further, but basically A manufacturer gets assigned a range of addresses, and so the MAC address has a component that relates to the manufacturer of the device, and then there's like a serial number that comes after it. So this is actually, on a worldwide basis, this is unique. This is something different than the TCP address that you're probably more familiar with, which is at the network layer. Now, generally speaking, this is hard-coded. There are, however, tools, there are ways that this can be spoofed, that this can be changed, that you can mask what your MAC address is and replace it by another MAC address. That's definitely something that, somebody with mischievous intentions, let's call this person a cyber criminal, would want to do. This is something that we do when I'm teaching, hands-on cybersecurity in a lab setting. It's something that we show students how they can do that. There's tools, you can Google it. It's not really that hard. However, for the script kiddies, the novice person who wants to commit some kind of crime using computers and doesn't really know what they're doing, this is something that they're not going to think to change, or that they're not going to know or figure out how to change that. Then we get to layer 3. So layer 3 is the network layer. So this is the layer that is responsible for the logical implementation of the network. So it's something that we'll be talking about more, that you can certainly read more about in the book, hopefully in previous courses as part of your bachelor's. You've learned a lot more about TCP/IP networking, how that works, how that is broken up into different parts. There is a network part that identifies the local area network, and then there's a host part that identifies the specific machine on the local area network. And so at the network layer, if the network part is not the same as the network that you are currently on, then it will know to send the packets at the network gateway device. We could think of a router being a network gateway device, your classic network gateway device. And so it'll send it there using the data link, using the physical layer. And then when it gets to the router at the physical layer, it'll go to the data link. It will go to the network, and then we'll say, hey, this machine that I'm trying to connect, this device that I'm trying to connect to, is on a different network. So how can I find that network? That's all. That stuff is happening at layer 3. But when one layer 3 on one machine is talking to another layer 3 on another machine, it's going down to 1 across the physical media, up 1, 2, 3. And then some kind of decision-making process happens. It might decide it needs to send it on another network. Then again, it'll go down 3, 2, 1, and then across. So that's really the key layers, 1, 2, 3, the key layers at the network part of the model of how machines connect to each other. Then as we get above that, then it has more to do with the host, the machines themselves who are talking to each other. So at layer 4, the transport layer, this is really taking the information, breaking it down into packets, and making sure that we have some kind of mechanism, depending on how much of a guarantee of deliveries that we need, making sure that is structured and organized so that information will get across, and that we can guarantee that the information is properly reassembled by the host on the other end of the communication. So this is all happening at the layer 4, the transport layer. The layer 5, the session layer, is responsible for maintaining communication sessions between machines. So it creates, it maintains, it disconnects communications that are taking place between processes over a network. So for example, perhaps I'm connecting to a database server and I'm doing a query on the database, and so I need to open the session. Maybe I'm using some kind of terminal emulation. I'm actually using a virtual machine running something on another machine and just viewing on my screen, viewing the results. All this kind of stuff is typically happening at this layer, at layer 5. At layer 6, the presentation layer, this is responsible for the coding of data. So things like file formats, how characters are represented, encryption, all of these things typically would happen at layer 6. And then the application layer, so this is where we're interacting with the end user. So if you're, right now you're using a computer and Windows and you're watching this video on, I don't know, maybe on YouTube or maybe through our Moodle system, through a web browser, you're at layer 7 right now. This is where you are, where the user is interacting with the machine itself. But then, of course, layer 7 is talking to 6, to 5, to 4, to 3, to 2, to 1, sending the information across the physical network. And the other end is going back up, 1, 2, 3. And maybe you're connecting to a video server at YouTube. You're just going all the way back up to layer 5, and then that's where that is happening. And it's sending back the information. And again, you're seeing it at layer 7. So this is just a really good way if we want to, get some kind of theoretical understanding of how machines, how hosts are talking to each other, how applications are running, and perhaps for diagnostics purposes, we might want to do something. So that's the model that we'd be using for that. So very important. It's something that you should remember by heart. There's different techniques. I have to... I forget what the word is for this. Minimum, I don't know. But just like an acronym that I use. So all people seem to need data processing. APSTNDP. All people seem to need data processing. So this is how I remember it. Because I'm old school and data processing is how we used to call computers and management information systems and business technologies way back in the early 80s when I started doing this kind of stuff. Another one is please do not take the salami pizza away. So PDNTSPA. Please do not take the salami pizza away. Okay, you can come up with your own stuff, but those are the two that I know. Again, I use the first one, but if you can remember that, then you've got the OSI model down pat, and then you can always remember it for the rest of your life. And the rest really goes through experience. So when we're talking about networking, we're really talking about two kinds of networks. So the local area network, or LAN, and that's our local network. So that's the typically less than 1 kilometer geographic distance. So the local area network is, if this was a normal year and we'd be doing class in a normal way, we'd be sitting in the classroom and we'd talk about the local area network being the actual classroom that we're in. Is one local area network. And a local area network, so it has a network address. When we talk about TCP/IP, has a network address, so the first part of your TCP address is the same. And we're talking about the layers before, right? The OSI models. So we're like layer 3 and below, and we're on the same physical network or wireless network, and so that's a very small geographic area. Then when we talk about a larger geographic area, we talk about the WAN, or the wide area network. So the best known WAN is the internet. The internet is a wide area network, but a lot of companies may have, used to have. When I was learning this, we'd have private wide area networks. Company would set up their own wide area network. Today, except for maybe some very large utilities or law enforcement agencies, or maybe the military, no one really has their own wide area network now. We all use the internet as a wide area network, and we set up a private network within the wide area network using virtual private networks, or VPNs. But typically a wide area network is a large geographic area. So really anything we used to say 35 kilometers or more. In reality, anything bigger than a LAN is going to be a WAN. And as soon as you have like two LANs connecting together, of course, there's some variations. We don't really talk too much about them anymore, but there's a campus network. So like, at the university, all the buildings, everything's connected through a wide area network, but it's on the same campus. So we call this a campus network. We might have a metropolitan area network that's within the same city. So at the university, we have two main campuses, one out in NDG, one downtown. Those would be through a metropolitan area network. In some cities, there's like in Paris, for example, there's a metropolitan area network running through a fiber that's running around the boulevard périphérique, the sort of the beltway around Paris. Has a fiber optic, so companies build towers all around that highway, all around that road. They can just connect into the fiber. They're connected to the metropolitan area network. But for us, we're going to keep this simple. We'll talk about the local area network when we're talking about a small connected network, maybe cabled, maybe wireless. And then when we start adding routers and stuff, we're really getting more into a wide area network. So typically a larger area. So as I mentioned before, the best known wide area network is really going to be the internet. The internet being an open network, so it means that really anybody can connect to the internet. No one actually owns the internet. Companies own routers. You maybe have a router at home. The university has a whole bunch of routers here. And one of those routers is going to be connecting our network through a router to a whole bunch of other routers and through a internet service provider or a telecommunication company. Universities here in Quebec, we have our own service provider to connect to the internet for all universities and post-secondary schools, so colleges in the province of Quebec. And then we're connecting to a larger Canadian network, Canary. But you can also connect to the internet through Videotron, through Rogers, through Bell, through TELUS, through a whole bunch of other service providers, large and small. So the thing is about that is that the internet itself, because no one owns it, there's no guarantee of privacy. The information, once it's out, it's out. So we don't really know. It was, and really originally, the internet really wasn't designed for security. Originally, it was designed, it started as ARPANET, right? You might know the story in the 60s. And it was a military network developed by the DoD in the U.S., of course, Canada being, very much connected with the U.S. military. We were at a very early point, we were connecting to the internet, early 70s. Here in Montreal through McGill, doing research and development contracts and stuff. But early on, because everyone knew everyone that was connecting, there wasn't a big concern for security. Security sort of came as an after fact. Once we started connecting, people, private citizens and private companies, and everyone started connecting to the internet, and it started to become really very global. And this really happened in the early 90s. Particularly with the arrival of HTTP, of the web protocols, and then eventually the web, and then eventually e-commerce. So really in the 90s, mid-90s is when this started to explode. And that's when really security became more of a concern. So when we're connecting to the WAN, we connect in different ways. Most of us at home, we would use something called a cable modem, and we'd be modulating and demodulating. That's modem, M-O-D-E-M, right? Modulator, demodulator. So we'd be converting at the physical layer, and at the data link layer, we'd be modulating ones and zeros into a signal that can be transported over a coaxial cable through our video, like Videotron or video service provider. DSL, so we're using digital subscriber lines. So we're using a device that is a digital device, but that is using phone cabling, full phone signaling, and converting into data packets that are compatible with SONET, with the phone system protocols, so that it can transfer information. This is typically what you would have a few years ago if you were a Bell customer. Fiber optics, so we're transforming into light. So we have a device that is generating a laser pulse that is being sent through a very, very microscopic optical fiber, so glass basically, through satellite. So we're uploading onto a geostationary satellite traveling around the Earth. Well, actually, it's traveling around the Earth at the same speed as the Earth is going. So it appears to be stationary from looking at it from the ground. And of course, it's at a relatively high altitude. And so in order to do that, and so we're sending using a dish, we're sending up information, transmitting to the satellite, and then it's transmitting the information back down. This is very good in different regions of the globe where you don't necessarily have a wired infrastructure that is needed for either cable, fiber optics, or DSL. Of course, there's a small delay, about quarter second, half a second, to send the data up and down. But, it's still pretty good. Dial-up is something that we used to do a long, long time ago. When I started in the 80s using the internet, we'd have a modem. You might see those in movies. It made a sound like, for the older students, maybe you've heard of fax machines. So it made a sound like a fax machine. Anyway, it would sync up with the regular, so it would transform the signal into sound. That's how it would modulate the bits and bytes. And then, of course, there's cell networks, 3G, 4G, now 5G networks. So very, very high speed phone networks that are being used. And this is particularly with 5G is really the way of the future. Very, very efficient way. We can set up a tower pretty much every 35 kilometers and we can cover a whole country. So if you're in, let's say, India or parts of the African subcontinent or in the Indian subcontinent, that's probably a really, really efficient way. It's much better than running wires. Much more efficient than using a satellite because of the delay of the satellite that I talked about. So the routers are connecting the different local area networks, right? And so we're going to have multiple routers, and we're going to set up different zones using our routers. So we're going to have, like we have at the school, we have routers in pretty much every floor of the building that are connecting all the different classrooms internally. And then eventually these are all connecting to a server somewhere. And then before we go out to the internet, we'll have another router. That's the border router that you see here. And its job is going to be to send stuff that has to go to the internet or receive information that's coming in from the internet, which is all going to go through some kind of logical separation, which is referred to as the firewall. So we're basically building a big wall to try to block as much as possible unauthorized things going through. It's not 100%, but it's an additional layer. And we're going to talk about over the next few weeks about different layers that we're going to want to build, and things like trust. And also I've added some videos that you can go watch that talk about these issues of trust, and particularly something called the zero trust architecture. So when we design our networks, how are we going to design the network so that it would be offer as much protection as we can. And so this is typically how most networks are going to be pretty much set up. So we're going to have, between us and the internet, so us being the internal network, we'll have our WAN, our wide area network internally, and then local area networks internally. And they're going to be managed by the interior router, and then we'll have the border router, and then we'll have firewalls connecting. At the local level, we're going to have, the router going out to the internet, but we're going to have switches that are going to be connecting the different local area networks, the different physical machines on the local area network. So the switch itself is sort of a traffic cop that's going to make sure that all the machines can use as much as possible, can use the local area network and have access to the bandwidth. Now, we're not, we'll talk about how Ethernet works and everything and how TCP/IP works. But just know that there's these issues of traffic that we have to worry about, making sure that if we're sending an electrical signal on a cable or an optical signal on a fiber, we need to make sure that we're not sending a whole bunch of different signals at the same time, because then we're going to get into issues of interference. Same with WAN, but similar to what in WAN as well, we get radio interference. But that's going to be the job of the switch. As well, the switch is going to offer some security aspects as well. We can do filtering MAC addresses and stuff, so that somebody couldn't just walk into the building and physically connect to the network and then bypass all of our security. But that's all of these things are happening at the switch. So today, all local area networks are using Ethernet. This wasn't true 20 years ago. Definitely wasn't true when I was taking these courses. When I was an undergrad, we have to worry about a whole bunch of stuff, a whole bunch of different types of network topologies. But today, there's pretty much only one. It's Ethernet, two, I guess, if we talk about wireless. But at the local area network, we basically have the Ethernet, which is the physical cable network. And then we have the wireless network. So at the physical layer, we have this Ethernet network is really handling how machines are talking to other machines, using a cable, and typically what we're using is a copper wired, unshielded, twisted pair UTP. And so we're connecting using like something that looks sort of like a phone jack. For those of you who are old enough to remember actual phones that are plugged into the wall, they have an RJ11. Well, we use something called an RJ45. I think in the classroom at the university, you typically see that on the professor's desk. It's probably the only place that would have a physical connection. These tend to disappear, but in office buildings, you still see them. So that's the physical layer. It's using something called a CSMACD, a carrier sense multiple access with collision detect. Basically, it's a one-way street, and everyone's traveling. All the data is traveling on this one-way street, and so there's always the possibilities that there's going to be an accident. That's the collision detect, and so it has a whole bunch of mechanisms in place to make sure that that everything goes well, and that if it detects a collision, it'll retransmit the data. And so these are all the kind of things that Ethernet is concerned about. So again, here, it's something that you guys should know about already. Hopefully. If not, you want to look into it. And this is at this level is where the MAC addresses come into play. So the MAC addresses are the physical addresses of these cards that I talked about before. So all of these computers using Ethernet are connecting to a device which is used to be called a hub. Now we have, I guess, what we could call a smart hub, which is a switch. So when I mentioned collisions before, these would typically happen on hubs, where perhaps all the machines tried at a given point in time tried to send data at the same time. Typically it has a pseudo-random generator, so that when somebody wants to communicate, it will listen. It'll see if there's anyone communicating right now, and if no one's communicating, it'll wait a random amount of time, and then it'll start transmitting. In the hope that no one else decides to start transmitting at the same time, hence the value of having some random number, pseudo-random, really, because computers are never really completely random. So it has some kind of algorithm that produces this randomness. And so this is how these machines are talking, right? And they're talking on this physical cable. They're talking through and all these devices are connecting into this sort of hub where everything is like a star kind of thing. So in reality, Ethernet is a bus, but it's physically looks like a star where everything is connecting into this hub. And so later on, when people realize, hey, you know, these collisions are really becoming annoying, and we're losing a lot of time, is there a smarter way that we can do this? And this is where the switches came into play. So the switches have a lot of intelligence built into them that minimizes the possibilities of these collisions. And also, because it has some intelligence built in, it also has some configurability issues. So you can configure them to, for example, for security purposes, maybe you want to filter so only known MAC addresses can be used. But there's all kinds of different filtering and security configuration that is possible there. And then, of course, in order to create some kind of additional security, we've decided, hey, wouldn't it be nice if we could actually create a tunnel throughout this local area network and wide area network, and perhaps we can divide up these large local area networks into logically smaller local area networks. And this is where the VLANs come into play. So it's all the same physical, but we're breaking it up into logical groups. Perhaps we can do some encryption, some tunneling, all kinds of different security things that can happen here. And also we can reduce the possibilities of collisions. We can reduce the possibilities of people listening in to what's happening on the other machines on the network. So these are all the way that we can physically isolate or logically isolate what's called a broadcast domain. So we'll talk about TCP/IP in a few minutes, but we can broadcast messages on the whole network, local area network. But if we can logically separate it, this isolation is going to reduce the network traffic, but also give us some security benefits as well, potentially anyway. So Ethernet is the physical. And then the logical, we're getting into TCP/IP. So the TCP/IP is the transport control protocol and the internet protocol that we're going to be using. So I mean, again, here there used to be a whole bunch, but now there's really nothing anymore. Everyone is using TCP/IP. It's really what we would call the de facto standard for this. So it's really a suite of protocols that handles how information is going to be sent and how we're going to make sure that it's sent and all the different things that we're going to be doing. So it's not just one; it's a whole bunch of different protocols that are working together as a coordinated ensemble. And so it's really what we're all doing. It was originally designed to be reliable and fault tolerant. It was never really originally designed to be secure because, as I said before, everyone knew everyone that was connecting, so really not a big deal. So TCP/IP is really divided up into two parts: the TCP, so the transport control, and then the user-defined, the UDP. So really, what we could say between the two is UDP has no guarantee of delivery, and TCP has a guarantee of delivery. So at if we actually look down and using things like Wireshark and different tools that you're going to use in the labs, you're going to actually see traffic going through. But when I'm sending a packet, if I want to make sure that it got there, I'm going to want to receive some kind of acknowledgement, or also referred to as an ACK. Then I'm going to use TCP. When I really don't care, I just want to send information, and I don't care because if it doesn't get there, I don't want to resend it. I'm going to use UDP. So imagine, for example, that I'm streaming video, like this video conference that we're doing right now. If for some reason there's a problem and some of the packets don't get through, do I want to keep trying to resend these packets, or I just want to skip it and move on? So because otherwise, you might get like an echo, you might get like a weird video conference. Whereas, it's okay if there's a few little glitches, but I just want the whole thing to flow. Then I would want to use UDP for this kind of thing. So TCP, if I'm sending a file, I'd be using the File Transfer Protocol, FTP. If I want to send web pages, I'd be using the Hypertext Transfer Protocol, HTTP. Email, SMTP. If I want to run a terminal session, maybe you guys are doing some Linux stuff, and you'd want to open a terminal on a different machine, that's Telnet. There's one called DNS, the Domain Name Services. When you'd want to transfer an IP address to an actual machine name, that's DNS. Hopefully you know all about DNS at this point. If you don't, please Google it and go watch some videos how DNS works. Simple Network Management Protocol, SNMP. So this is information about, maybe errors or faults or issues on the networks and help us remotely manage some machines on the network. The DHCP, so this is Dynamic Host Addressing Protocol. So if I need a machine, a host needs to have an IP address. Maybe I don't want to have a dedicated address because the number of addresses are limited. I want to dynamically assign an address when somebody connects. Like, for example, when you're connecting at the university with the wireless area, the wireless network, we don't want to have a dedicated IP address for every machine because there are 50,000 students at Concordia. When you bring a machine, we'll give you an address with DHCP, and when you leave, that address is going to be freed up and somebody else can use it. So that way we don't need to have 100,000 possible IP addresses. So these are the kind of things that we're working with in UDP. So that's the protocols that we're using, and so the protocol is divided up in a whole bunch of different things. Now, the TCP/IP itself is using IP addresses. Most of us use version 4 of TCP/IP, IPv4, which is a 32-bit address. So it's divided up into 4 blocks of 8 bits, right? Which is like the IP address that you're used to, like 192.168.10.1. Across the network, this is going in binary, but that's the most common structure that we're going to have. There's the host part. There's a network part. This is how we know, if you remember what I mentioned earlier, if the machine is on the same LAN as us or if it's on a different LAN. So the way we know the difference with that is the mask, the network mask, or also known as the subnet mask. Whatever is on the network side is on the same LAN as us. Whatever is on the host side is on the same LAN as us. Whatever is not on the same network is on a different network. So it's got to go through the router. And then because we're running out of TCP addresses in IPv4, people came up with IPv6, which is 128-bit, which gives us a lot more addresses also because it was designed at a later time. A lot of security aspects also were built in. Still, not everyone is using IPv6, but it's a really interesting way to go, and certainly more and more is going to be adopted. So the DHCP, like I said before, this is how most computers on networks today work. So if I connect a new machine, it'll send a request, and then it'll come back and it'll give me an IP address. So TCP/IP uses ports. And there's well-known ports. So there's really a whole bunch of ports. I think it's up to 1,023 that are assigned by the Internet Number Administration Group. So there's the Internet Engineering Task Force, the IETF, that has this numbering protocol, and they've reserved everything up to 1,023, I think, is reserved. And then, of course, there's some that are known and that are above that, but typically those are always going to be the same. So because otherwise things like email wouldn't work. If we didn't have some kind of agreement that for mail transfer we're using port 25, then there's going to be some issues. Same as, there's going to be some problems. If we don't all agree that web is happening at port 80, then we wouldn't know. If I'm sending a request to a web server, I wouldn't know what port to send this. So, your IP address is like your mailing address, and your port is like the postal box within the building, what your office within the building, right? So So this is ports, and so ports is how TCP/IP knows once it gets to the host, when it gets to the right machine, it knows where to send the information on that machine. That's the port. And so there's these lists of, well-known ports. But again, here in the labs, when you'll be doing some of the exercises and trying to look at protocols and information going across, these are the kind of things that you're going to be doing. There's all for security reasons as well. I mean, this has some interesting capabilities, but will be better seen in the labs than just me telling you about it. So a few more here. DNS is 53, the web 80, Windows machines or secure stuff, hypertext secure on 443. Let's see what else. NetBIOS, so I was talking about Windows stuff on 137, 138, 139. Let's see what else. Telnet on 23, etc. So some of these more common ones, the ICMP, the Internet Control Message Protocol. This is the protocol that we use to send information to see if a machine is there. For example, we do a ping. Ping is this kind of thing, ICMP. Again, in the labs. So if I know what the ports are, I can actually use this information to do reconnaissance. So I would do recon. I'd try to gather as much information as I can about a network if I want to try to attack a network. I would definitely want to point out to you that, it is a criminal offense in Canada to try to hack into somebody's network or to use computer resources without the permission of the owner of these resources. And here, when you guys are starting to learn about this, you're starting to know just enough to get into a lot of trouble, which you don't want to do. You can do all the hacking you want on your own machine, in your own house, in your own lab, perhaps by disconnecting yourself from the internet just to make sure you don't screw up. But please be very, very careful, because we are getting to a point where you're starting to know just enough to get into real trouble. So recon is this act of gathering. You don't want to start doing recon on all the computers at the university or people in your building or in your block or in your neighborhood. But this is the first step, is trying to get as much information as you can about what's going on. And how you're going to do that is by using IP addresses and trying to scan a local area network and trying to see what are all the ports that are open on the different machines on my local area network. And then you can also do eavesdropping. So you could basically use something like some of the software you'll be using in the labs, Whiteshark and things like that, to try to get to listen in what's going on your network. Denial of service is when you're just sending packets through the network to try to just make the computers super busy. And that's, a very easy way to bring down the network. Even better, you can do it and have multiple machines sending information across the network, and that's the distributed denial of service. Or you can do the same thing with phones that he does. So some of the basic tools that we're going to be using and that we need to know about and that we'll be talking about certainly today. So the firewall, the VPNs, and the NACs. So let's start with the firewalls. I talked about firewalls already before, right? A firewall, think of it like a wall, and the wall has some kind of gatekeeper, which is basically rules, the business rules, kind of. And it's really looking at everything that's coming to the firewall and asking a question: are you allowed to go through? Yes or no? And there's going to be a whole bunch of rules that are going to be applied to know, well, if something should go through or not go through, etc. And we can have multiple firewalls, so we can segregate, right? So we can split up our network into a whole bunch of networks so that we can make sure that traffic is not going through. So flood guards, we might have rules that limit the traffic, so try to prevent the denial of service attacks I was talking about before. Right, separating up the networks into different networks. So making sure the traffic doesn't get around one network to another network, or preventing that maybe there'd be some kind of loop so that information was just, staying and generating a whole bunch of useless traffic and slowing down our network. Most common way to use a firewall is going to be through packet filtering. So we'll be looking at the different packets that are going through with the TCP/IP addresses and the ports, and looking at where is this coming from, where is this going to, and is this something that I might want to go through. Sometimes we'd also want to look at go much deeper. So we'd be going into a stateful inspection firewall, which remembers information about the status of a network communication. So once the firewall receives the first packet in the communication, the firewall remembers that that session until the session is closed. So this type of firewall doesn't have to check its rules each time it receives a packet. It only needs to check the rules when a new communication session starts. So this is a little bit more efficient than just going at packets. And then an application proxy firewall goes further than stateful information firewall. It doesn't actually allow packets to travel directly between systems on the opposite side of the firewall. It opens a separate connection which each of the two communication systems then acts as a broker, as a proxy between the two. So this provides an additional level of protection because the firewall can analyze information about the application in use when making decisions to allow or to deny traffic. Of course, the big thing here is this is going to be slower. So I'll give you different ways that we can deploy this. We can put firewalls at the borders. We can create artificial or screen subnets. Typically, we'd have only one of those that is available from the outside, which would be a demilitarized zone or DMZ. Or we can have just multiple layers of firewalls set up. So this is what the border firewall would look like, right? So this is really how typically this would have been done when firewalls first started to be implemented. This is how we used to do it, right? Setting it up at the border and then taking for account that everything going inside was okay. But then we didn't really understand. I think back then that we spend all of our energy protecting ourselves from the outside, but we didn't really understand that a lot of the issues really were internal, and we should really spend a lot more time thinking about what's going on inside. And then we started setting it up a little bit differently with screen subnets, and that's when we came up with this concept of the DMZ, right, where we have this network. So everything that's coming from the outside or even from the inside, all the servers and everything would set up in this zone. So it could allow us much better control at that level. And then unified threat management. So if we want to use filters and filter web traffic on the routers and on the switches, looking at what's going on inside, looking also at the contents of messages. So inspecting things like inspecting the contents, looking if there's maybe a Trojan horse or malware or something inside of it. So not only do we want to look at from a network point of view or a layer 2-3 point of view, but we also want to look at the other layers all the way up to layer 7 to try to limit what we're actually going to be allowing to go through. So another thing that we want to look into as a very common way of creating security is the virtual private networks or VPNs. So here we want to look at, if we have maybe employees working from home, how can we create an encrypted tunnel? So because all this information is going across the internet, so can we make sure that the information that we are sending will be coded so that if somebody sees the information, they can actually make sense of it. So this would be useful to connect two remote offices using the public network like the internet, or maybe these days more for people working from home, and we want to make sure that the information is secure when we're doing that. So the three basic technologies, secure sockets, SSL or TSL, point-to-point tunneling protocol, PPTP, or IPsec, the Internet Protocol Security. We're not really going to go in depth at this point into what these are, but just that you know that they're there. So NAC, network access control, another thing that we'd be doing, right? So adding more security by physically checking when a device wants to connect. So we'd actually be looking at how this is connecting. Okay. I do want to talk a little bit about wireless networks, because that's the most common way that we're going to do this. That we're going to connect to local area networks these days. Everywhere, even out in the cities, out in the airport, in cafes, probably within your home, but definitely more and more with businesses. And so this is when we're using at the physical layer, we're using radio frequencies, RF. And so here there's not a physical network in the sense, because it's radio frequencies, which is the media, is the air around us. And so the big thing here is that it doesn't stop at the wall, right? So if somebody could go out in the parking lot, anyone who's within the range of the radio frequencies can connect to it. So this brings a whole bunch of different new problems. And if we're sending data, we got to make sure the data is going to be encrypted. And so there's a whole bunch of different encryptions. Of course, the old WEP, which is really totally insecure, and you can hack in about 30 seconds. But there's a whole bunch of other, like Wi-Fi protected access, WPA. And so that's going to allow us to add different layers of security, of encryption to the data. And we can also, make sure we're not broadcasting our addresses everywhere, and we can also filter MAC addresses, although that can also all of this can be hacked anyway. But we don't want to prevent hacking as much as we want to make it really hard for people to hack into networks. And there's a whole bunch of other things that we can look into: the power level, the type of antenna we're using, etc. So there are a whole bunch of different tools there. So again, something that hopefully we'll have time to talk about more. And if something that interests you, you can definitely, there's a whole bunch of videos and material that you can look into to that. So there we go. So that was the lecture for this week on networks. And so please do remember the OSI reference model. I think that's really important. It's going to make your life a lot easier if you understand, at least if we have like a common framework and language to use, that we make sure that we understand what we're talking about when we're talking about local and wide area networks. All right, so thank you. And don't forget to participate in the Zoom sessions, and to make sure that you read the book and do the exercises and the labs that are required for this course.